The history of AI is very interesting. We will only cover a more recent side of the history of AI. In 1980s, AI boomed from a few $1 million to billions of dollars. Hundreds of companies started building something known as export systems, vision systems, robots, and softwares and hardwares for their specific purpose. An example of a successful AI method is an export system known as R1, which was developed by DEC at that time in 1986. And it was saving the company estimated of $40 million per year. And by 1988, DEC had its AI export system deployed in more than 40 locations. So here's a summary. Here's the abstract of the 1980 paper R1, the export system used in DEC. Basically, what the export system did was whenever a new order came in, DEC had to figure out what parts of the computer parts were missing and add that to the order so that the order would be complete. And humans would need to spend a lot of time trying to figure out these missing parts, and R1 would be able to automatically, looking at the order, figure out what parts are missing, add it to the order so that the customers didn't have to wait for a human to figure out what is missing in their order to make it a complete computer system. And very quickly, nearly every major US corporation had its own AI group or was either using or investing in export systems back then. Before 1986, for quite some time, neural networks were out of focus. Once again, people applied backpropagation algorithm to many learning problems in computer science and psychology, and that caused great excitement again after 1986, and neural networks became interesting again. And currently, the neural network research that we have has bifurcated into two fields. One is concerned with creating effective network architectures and then algorithms and understanding their mathematical properties. That is, what we look at is more interesting ways of connecting neurons or coming up new theories on how interconnections between neurons work and so on. And the second is concerned more with using existing architectures and algorithms and simply carefully modeling empirical properties of actual neurons and ensembles of neurons. That is, building applications. So applications, and this is more of research into how neural networks work and coming up with new ideas. The reason this research is important because you will see that today there are various ways in which neural networks neurons can be connected. For example, if we simply have one neuron, this will be perceptron. If we add hidden layers, that becomes feed-forward neural network. If we have many hidden layers, that becomes deep feed-forward neural network. If we have recurrent connections, that becomes RNN. We have long short-term memory, GRUs. We have restricted Boltzmann machines. We have Markov chains, deep belief networks, and we have GANs. We have many varieties of neural networks right now. So it is important to continue this area of research and see what works and what doesn't. We saw that AI is a lot about thinking or acting like humans. Now, is it a good idea to stick to thinking or simply acting like humans? Let's see how we designed airplanes. We saw a bird flying in the sky and we imagined that we could build airplanes that could fly. So of course airplanes are we designed airplanes looking at how birds fly, but it's not just that. We came up with so many theories about um, aerodynamics. We came up with so many theories about how things fly, what flies and what doesn't, um, and we did more than simply looking at a bird flying in the sky to come up with working airplanes. In other words, we looked at nature to copy what's in the nature, but we did more than what was available in the nature to make things work. Another example is wheels. Not one animal in nature rolls around in a rotating body part. That is, no animal has a biological wheel. So if we were to simply look at the nature and build things that are only in the nature, we would never come up with wheels. In other words, there's a lot to learn from nature, but nature also has its own limitations. So for that reason, it is important that the field of AI not only stick to what's what the human brain can do or what's available in the nature, but go beyond what's out there. So considering that many people thought that the techniques of AI or the progress in AI must adopt a scientific method where people build on top of each other's work. So for that reason, now it is more common to build on existing theories rather than to propose brand new ones. Instead of saying, I know how brain works or how I know how brain does what it's supposed to do, people now compare existing works and treat AI more like a standard scientific discipline. And it is now a practice to base claims on rigorous theorems and hard experimental evidence rather than on simply intuition. And also to show relevance to real world applications rather than toy examples. And this makes AI adopt a scientific method. So it has now become more of a scientific field rather than where people propose various unproven ideas. And one example of that is the progress in speech recognition. In 1970s, a wide varieties of different architectures and approaches were tried, mostly ad hoc and fragile. In other words, one researcher would come up with one idea that said, "I know how speech works," and he would model or trying to come up with a theory about how human brain or how we can talk and speech works. Another person would come up with second idea, and the theory behind how we do speech, and so on. So these were not working ideas, but rather theories of how human speech works. However, in recent years, something known as hidden Markov models have become the dominating technology in this area. And hidden Markov models are methods within AI which do not use or are not inspired from human brain. So brain, we would have neural networks, but human Markov models um, are not the copy of the human brain. Rather, they are purely mathematical based models that can do learning. And such a success of hidden Markov model, where hidden Markov model are in no way what the human brain does, but it is very successful in understanding speech and so on. And this has allowed speech researchers to build on mathematical results developed in other fields. In other words, now people can refer to what others have done in other fields and use that to improve hidden Markov model and techniques that emerge from that. And hidden Markov models are generated by a process of training on a large corpus of speech data. This ensures that the performance is robust because now we are not relying on somebody's theory of how the brain works, but rather on data and learning from data. And similar gentle revolutions have occurred in robotics, computer vision, and knowledge representation, where we don't necessarily simply look at how the brain works and base our implementations on those theories, but rather look at the data, come up with mathematical theories and mathematical principles to develop methods. Since 1995, we are now able to build many intelligent agents that can do a lot of things. And that's primarily because some influencer founders of AI have expressed discontent with the progress of AI. And what they think is researchers in AI should put less emphasis on creating ever improved versions of applications that are very good at specific things like driving car, playing chess, or recognizing speech. Instead, what they think is we should rather focus on something else. That is, don't focus on these specific things because we will naturally, the AI methods that we build will naturally become very good at these things. Instead, they believe that AI should return to its roots of striving for machines that can think, that can learn, and that can create. So this effort of looking into techniques of AI that rather can build machines that can think, learn, and create is known as human level AI or HLAI. And of course, it requires a very large knowledge basis to be able to do this. Now, within HLAI or human level AI, there is a subfield known as artificial general intelligence, very popularly known as AGI. And the field of AGI looks for universal learning algorithms and learning algorithms that can enable learning so that we can act in any environment. So the idea behind AGI is not just focus on this gradient descent based algorithm or simply on the backpropagation algorithm, but look at something bigger than this. Are there other ways of learning? Can we do better than what we have been doing using these learning algorithms? So that's the focus of the artificial general intelligence. Since 2001, the availability of very large data sets has changed the way we do AI. In the 60-year history of computer science, we've always emphasized on algorithms and we put algorithms as the main subject of study. Some recent work in AI suggests that for many problems, it makes more sense to worry about the data and be less picky about what algorithm to apply. Now, the point is not that algorithms are useless. That's not the point. The point is that we may now need to focus more on the data and less on the algorithm that we want to apply. In other words, say for example, I have a problem A with a lot of data, and I want to solve some problems, solve this problem A using the data that I have. I may have option of algorithm X, algorithm Y, and algorithm J. Maybe one of them is extremely challenging to implement, complicated to implement, but may offer 2% advantage, right? So the question may be, should I focus on implementing this algorithm and skip these easier algorithms X and Y and try to spend most of my time implementing this algorithm and testing it because it offers 2 or 3% improvement over all other algorithms? The answer is no. If we have a lot of data to work with, it may be a smarter idea to spend more time understanding this data, using it appropriately, and pick any one of these algorithms, X, Y, or Z, as long as they have similar performance or comparable performance, and build our applications to solve this problem A. And here's an example. So this paper is a 2007 paper. The challenge is, so for this paper, what the authors did was they took a picture like this and they removed certain parts from the image. And what they want to do is use the remaining picture to reconstruct the rest of the image. So they used a lot of images, millions of photographs like these, and they were able to achieve reconstructions of scenes like this, where the authors could generate the remaining part of a scene like this. So, for solving problems like these, which may be relevant for self-driving cars, for medical applications, and many other purposes, algorithms are not important. What's important then is if you have more data or a lot of data, then this problem becomes trivial, or the choice of algorithm doesn't really matter much. So AI today faces a problem known as knowledge bottleneck. In other words, if we have, let's say, a lot of data and here's our program, we are only able to learn a very little from this data and encode into our programs. So if this data actually had a lot of knowledge, we are only able to take a subset of it and put it into our program. So this knowledge bottleneck problem is how to express all the knowledge that the system needs. So my system needs all of this knowledge, but I'm only able to capture a little bit from the data and incorporate it into my program. And the work that I just previously showed, works like that, suggests that knowledge bottleneck in AI may be solved um, by many applications, by learning methods rather than hard-coded knowledge engineering techniques. In other words, if I have a learning algorithm that is powerful enough to learn from this data, then the algorithm will automatically extract all of these knowledge in my data without having a bottleneck. Let's look at some of the state of the art of AI. Already in 2005, a robot known as Stanley was able to sped through this a terrain of desert of 132-mile course to show that driverless vehicle driving is possible. Now with Google's AI, Google, we can make automatic calls to local businesses. We have now really good autonomous planning and scheduling AI methods. 100 miles from Earth, away from Earth, NASA's remote agent program became one of the first onboard autonomous planning program to control the scheduling of operations for spacecrafts. Google was able to win the game of Go, a really challenging game. And we saw that in the news a few years ago. Last year, Google's AlphaFold method won a protein folding competition known as CASP. Similarly, we have made a lot of progress in identifying spam. For logistic planning, we have AI has made a lot of progress. In robotics, the iRobot Corporation that makes the Roomba vacuum cleaner had already sold millions of their vacuum cleaners. For machine translation, now we know that a computer program can automatically translate from various languages, from one language to the other. In summary, in this chapter, what we saw is different people approach AI with different goals in mind. Two important questions to ask when trying to define AI are we concerned with thinking, or are we concerned with behavior? Do we want to model humans, or do we want to work from ideal standard? Neuroscientists, we found that we saw that discovered many facts about how the brain works, and the ways in which our brain is similar to and different from computers. AI has advanced more rapidly in the past decade because of greater use of scientific method in experimenting with and comparing approaches.